Hello everyone, another day, another lesson, new unit. We're going to start on logarithmic functions, so have a read through all of that. Okay, uh, let's talk about the story of logarithms. Logarithms were invented and first introduced in 1614 by John Napier, a Scottish landowner. Um, Other interesting factoids about John Napier, but what do logarithms do? They allow us to represent and understand quantities in science that change over vast ranges. Um, we're going to talk about like seismology and Richter scale as an introduction, but if you've taken chemistry, you know what pH is. And pH is measured on a log scale. Okay, so we're going to dive deep into logarithms, this unit, to see how they work. Seismology is the study of earthquakes. A seismograph measures the amplitude, so amplitude of a seismic wave from earthquakes. These waves can vary from an amplitude of 100,000 microns, a moderate earthquake, to an amplitude of 100 million microns, a major earthquake. So up to this point, you might have heard on the news earthquakes happening all around the world, and they might say something like a magnitude 7 earthquake of magnitude 7 on the Richter scale. You've heard that. Well, where does that Richter scale come from? Well, earthquakes can also be measured in amplitudes of hundreds of millions of microns, possibly. It's difficult to express the vastly differing magnitudes of earthquakes when the span of values is so large. To go from 100,000 microns to 100 million microns, that's a lot of space. Logarithms, as we'll see in our numerical example below, compress the span of values into a set of numbers more manageable and understandable. Can you imagine scientists, or you read or you listen to the news or see the news, and they report an earthquake with a peak magnitude of 100 million microns struck this area. Like, you'd pause and think, like, what the heck does a 100 million micron earthquake feel like? Like, you have no idea. Like, it's such a large number that you can't wrap your mind around. What is that? I don't get it. Nobody except seismologists would actually understand what that meant. Let's do a little exercise here. We're going to evaluate using the log buttons. Take out your calculator. For now, everyone has a basic log button. So you look on your calculator, it says log. That stands for logarithm. Okay, it's base 10. Don't worry about the base for now, but it's base 10. So all you do is press log and 10, close the bracket, I get 1. So we're going to do the same for the others. If you do log 100, so to go from 10 to 100, right? This is 10 to the 1. This is 10 squared. What do you think is going to happen? It's 2. We're going to go from 10 squared to 10 to the third, but we're going to take the log of 10 to the third, so log of 1,000. Any guesses? 3. You got it. What do you think is going to happen here? 10 to the fourth. Log of 10,000. Surprise, surprise. Log of 10,000 is 4. Next one. 10 to the fifth. If you're going to guess 5, correct, right? So let me do it on the calculator. Log of 100,000. Okay. I'm going to just show you something real quick before we keep going here. Right here. An amplitude of 100,000 microns, that's a moderate earthquake. Well, now you know, log of 100,000, that's 5 on the Richter scale. If you ever wonder where that Richter scale number comes from, there it is, folks. Okay? Like magic. Look at that. Log of 1 million. Well, that's 10 to the 6. Well, I know that's going to be 6. Log of 1 million. Log of 1 million. 6. Okay? 10 to the 7th right here. Log of 10 million. Well, that's 7. Log of 100 million. 1, 2, 3, 4, 5, 6, 7. I can count the zeros. Well, we know that's 10 to the 8th, right? Log of 10 to the 8th. That's 8. Log of a billion, you got it, 9. Well, if you're like looking at this, you're like, well, Mr. Kim, that's Richter scale right there. Look at those Richter scale numbers. What do you notice about the logarithms? Okay, pause here. What do you notice? Well, I pointed this out. If I take the log of 10,000, well, that's like saying the log of 10 to the 4th, right? 10 to the 4th is 10,000. Well, when I take the log, somehow I get the exponent in return. That's deliberate, right? That's what you should notice, is this something, there's a relation between logarithms, and exponents. So that's all I want you to get out of this little exercise, relation between logarithms and exponents. There's a special relation between it, okay? We'll find out soon enough. The above series of numbers are values on the Richter scale. Well, you got it, right? It is easier and more relatable to compare an earthquake of magnitude 8 versus a magnitude 7, right? This one, I'll give you the answer, but you'll be able to calculate something by the way later when we're doing the end of the unit, when we're solving logarithmic equations and doing application problems related to logarithms and exponents. For a magnitude 8, we know that's 10 to the 8th microns in magnitude, right? Magnitude 7, we know that's, right here. That's 10 to the 7th. If I divide the two, I can find out how much more intense a magnitude 8 earthquake is than a magnitude 7 earthquake on the Richter scale, okay? So I'll just use properties of exponents. Our quotient law, same base. I can subtract the exponents. So a magnitude 8 earthquake is 10 times more intense than a magnitude 7 earthquake. Okay, if we graph this on a logarithmic scale, a non-logarithmic scale, okay, this is graphed on an exponential scale. This is an exponential function, okay? You should remember this from last unit. This looks like an exponential function, right? Okay. Look how crazy that graph looks. Look at the scale of this. We go to 1 billion. That's 1 billion, folks. 1 with 9 zeros. All the way down here, 10 to the negative 1. 10 to the negative 1, that's 1 over 10. That's 1/10. Look at this crazy scale. Look how much space there is. Logarithms will shrink that scale down to something more manageable and readable. So when you look at the logarithm of all these values, it'll just be a straight line. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? Okay, so if you ever wondered, here's a seismograph, like a representation of what a seismograph might show for earthquake, like intensity readings. Okay, amplitude of seismic waves, so the shock waves that you're feeling. If it's a 100,000 micron wave that it's measuring, amplitude, right? So this is amplitude is like the height of the wave. Okay, we'll go over that in trigonometry later, right? Amplitude is the height of that wave. Well, you could say, well, hey, that earthquake I heard about, it was 100,000 microns in amplitude. And then your friend's like, what? Or you can say, hey, that was a magnitude 5 earthquake on the Richter scale. Okay, it makes more sense when you put it in terms of logs. All right, let's start defining the pieces parts of a log by talking about logarithms, in terms of this idea of inverses. Okay, recall the definition of an inverse. Okay, I put in apples through a function, I get lemons, but I want to inverse the lemons that I made. Well, I get apples in return. This is like a funny pictorial way to understand what an inverse is. Another way to think about inverse is, um, I put on my socks and then I put on my shoes. What's the inverse of that? Well, the inverse of that is I take off my shoes and I take off my socks. You're back to where you started, right? Or sorry, you're back to where you started, but you're doing the reverse of what you just did. Mathematically, this is how we represent an inverse. You're switching the x and y values. Okay? What is the inverse of the equation for y equals 2x plus 1? Well, I'm switching the value. So I'm going to, instead of y, I'm going to put x. Instead of x, I'm going to put y. And I'm going to say x equals 2y plus 1. If I solve for y, I can say y equals 2x plus 1 is the inverse. Oops, you can say it either way, but I'll say it this way since we did it this way. Y equals x minus 1 divided by 2 is the inverse of y equals 2x plus 1. Or likewise, you can say y equals 2x plus 1 is the inverse of y equals x minus 1 divided by 2. Okay? Using your knowledge of the inverses from the transformations unit, whether you covered inverses in transformations or you might have covered inverses in function operations, okay, we still understand how to do this based on this example here with the linear example. Sketch the inverse of y equals 2x. So remember, so this is like a mapping notation. We're transforming this graph by switching the x and y coordinates for each other. So we're doing yx instead. So instead of y equals 2 to the x, we get x equals 2 to the y. For now, you can generate a table of values by hand. So you can pick like a value x equals 1, then you'll get y equals, well, let's just do this. Pick values for y, since we don't yet know how to solve for an exponent, sorry, a variable that's an exponent. So pick values for y, and then get values for x. So you gotta kind of do it backwards until I can teach you how to evaluate exponential equations using logarithms. Okay, so you can pause, generate a small table of values, and see what this inverse function looks like. Okay. On this graph here, I'm going to plot some key points. That's 0, 1. This is -1, 0.5. Okay. This is 2, 4. Okay, this should look familiar. This is your standard exponential equation. Okay, and then this is 3, 8. So folks, if I'm swapping x for y values, well, do exactly that, right? Instead of 0, 1, I'm going to go 1, 0. Instead of -1, 0.5, I'm going to go 0.5, -1. So 0.5, -1. Okay. Instead of 2, 4, I'm going to go 4, 2. Instead of 3, 8, I'm going to 8, 3. 6, 7, 8, and 3 right there. Okay. So again, let me do these. I'm going to do the inverse one in red. Okay. So this is the graph of y equals 2 to the x. So your standard exponential equation. And then in red, this is your graph. Okay, nice and neat, smooth curve. This is your graph of x equals 2 to the y. Okay, I should back up. I told you to generate a table of values by picking y values and x values. Well, that was kind of a tedious way to do it. You could have done it just the way I just did it, where you find these points and just swap the x and y values. Okay, that's better. All right. This is for later, but you'll see that there's a mirror line, right? Remember we did reflections and stretches? Sorry, we did reflections, right? This is the mirror line when you do an inverse of a function. You create a mirror line, and the mirror line looks like this on an inverse function. Well, the mirror line happens to be the equation y equals x. And there's your mirror line, right? That's the equation y equals x. Okay, so I'm just going to sketch that in, y equals x. Okay, let's answer a couple questions. Write an equation for the inverse function. Can you isolate this? So, yeah, here it is. How do I isolate y in this equation? Because we usually write functions in terms of y. We'll show you how to do this later, but this is how you do it. Log base 2 of x equals y. Just like that. Okay? You can actually graph log base 2 of x equals y in your graphing calculator. It will look like this, what we just graphed. Okay? Because this you cannot graph in your graphing calculator because everything has to be in terms of y. Okay? Let's take a look at a couple of key characteristics here. Y equals 2 to the x. What's the domain? X such that x is an element of all real numbers. Okay. Okay, what about the inverse? Right? Well, let me do this. Let's do the range first. Okay. Y such that y is greater than 0. Y is an element of all real numbers for the exponential equation, right? So you can see that. For the inverse, if we're swapping x and y values, then we're also swapping domains and ranges. That should make sense. So the domain, without even looking at the inverse graph, I'm going to write it in as that, right? So the domain is going to be x such that x is greater than 0. X is an element of all real numbers. If we're swapping x and y values to generate an inverse, then it should make sense that their domains and ranges swap. Well, look at this. Oh my god. So I'm going to back up here, folks. I totally botched this graph. It should not look like this. There should be... Okay, my apologies. That's me being sloppy. This graph, it actually approaches x equals 0 like that. There's an asymptote. Okay, that makes more sense because when I'm writing this domain, you're like, well, that doesn't make sense. Okay, hopefully it makes sense. I fixed this. Fixed. Okay, sorry about that. All right. Back to domain and range. So you can see that the domain is x is greater than 0 for the logarithmic function. Let me write it in the color so it's visually more appealing here. So x such that x is greater than 0, x is an element of all real numbers. And that makes sense. There it is, right? Everything greater than 0 for the domain. And then the range is going to be the domain of the inverse function, right? So y such that y is an element of all real numbers. And you can see that that is true, right? All the y values will keep going up and down. Okay, x-intercept of the inverse function, x-intercept of the exponential function y equals 2 to the x, none. Y-intercept of the exponential function, 1. Well, what about the x-intercept of the inverse function here? Well, that's 1, okay, right here. And the y-intercept, well, it doesn't touch the y-axis, so none. And look at that. Okay, type of asymptote. Exponential function, we know it has a horizontal asymptote. We saw that in the last unit, horizontal. And then if we're taking the inverse, then it makes sense that the inverse has a vertical asymptote. Equation of the asymptote, y equals 0 for the exponential function. For the inverse, x equals 0, increasing or decreasing. Okay, the exponential function, this is an increasing type. We know this from the last unit. And the inverse is also increasing. You can see the direction that it's heading. Okay, let's make some connections. In the exponential function, y equals 2 to the x, if 2 is raised to the exponent 4, then the resulting value is y equals 16. Then the point 4, 16 lies on the graph y equals 2 to the x. In this case, x equals 4 is the input, the exponent. Okay, right there. And y equals 16 is the output value. On the inverse graph, x equals 2 to the y, if we substitute x equals 16 into the equation, we get 16 equals 2 to the y. Now we need to determine the y value to answer the question 2 raised to the exponent of what number is equal to 16? The answer is y equals 4. In this case, x equals 16 is the input, and y equals 4 is the output number, the exponent. Then the point 16, 4 lies on the graph of x equals 2 to the y. This introduces us to the concept of a logarithm, and the purpose of a logarithm is to write x equals 2 to the y with y isolated, which I briefly showed you up here, which sort of right now, for now, looks like magic, but we'll explain. Okay, howdy folks. Let's look at log and exponential graph. Let's compare the two. So let's do a quick review. So there's my standard exponential, increasing exponential graph, y equals. So my slider here is on 2, right? So remember this thing, right? We did this exploration. So I'm going to leave it on 2. That's our classic increasing exponential function with a base of 2. We learned about logarithms, and all logarithms is that they're the inverse of an exponential function. So when I turn on this exponential function right here, so when I press it, right, remember we did that whole thing where when we have y equals 2 to the x, right, so if we have y equals 2 to the x, right, we switch the x's and the y's, x equals 2 to the y, and then we can rewrite it as a logarithm, and we get y equals log base 2 of x, right? So log base 2 of x, right? So when we turn that on, this is what we expect, okay? And then we have that point right there, 0, 1. That's the y-intercept on the exponential function, so we should expect an x-intercept of 1, 0 on the logarithmic function. Okay, so we remember that. Okay, so let's take a look at, let me put in the mirror line right there. So that makes sense that that's the mirror line, right? And let me do a different color so it's not totally confusing. I'm going to do a dotted line, folks, and let's make it black. Okay, all right, so there's my mirror line. And so that shows you that the logarithmic function is the inverse of the exponential function. Okay. Okay, let's think of logarithms. Remember, I told you the story about John Napier, that Scottish guy. I guess he's the first recognized person. I don't know if anyone ever thought about logarithms before, but he was the first person recorded to think about logarithms and basically invent them for a specific purpose. And just like humans had to create or invent things like mathematical operations, basic ones like subtraction and division and multiplication and addition, right? Um, we had to create logarithms. So let's think of this like subtraction is the inverse of addition. So 7 plus 2 equals 9, and 9 minus 2 equals 7. Subtraction undoes the addition. Division is the inverse of multiplication. 3 times 4 equals 12. Well, 12 divided by 4 is 3. Division undoes multiplication. Logarithms are the inverse of exponents. We saw that, right? 6 squared equals 36. If I take the log base 6 of 36, it equals 2. I raised something to an exponent, but then I took the log of that same base, the 6, and I end up getting the exponent back. Logarithms undo exponents. The equation x equals 2 to the y can be written as y equals log base 2 of x. This is read as y equals log base 2 of x. The logarithmic equation undoes the exponential equation x equals 2y by isolating the y variable in the equation y equals log base 2 of x. This is unacceptable. Oh, why did that come out like that? I'm going to, let me fix that. Okay, let me do this. Look at that magic eraser. Ooh, magic eraser. Okay, let me fix that. Okay, folks, this should say log base 2 of x. Okay, I think your notes are okay. It's just my notes here that are a bit messed up. Okay, pieces, parts of a logarithm. Log base 2 of x, we know how to say it, right? Y equals log base 2 of x. Let's focus on the log base 2 of x part. The log, obviously that's the logarithm. The 2 is the base. Remember how when we did something like 2 to the x, 2 is the base? Well, guess what? So we don't confuse you, right? When they made the rules about how logarithms work for an exponent, so this is called a power. Remember the entire thing when you have base and an exponent? Base and exponent. This is all called a power, right? The base of the exponent, this is the base, is 2. Well, look at that. We also call it a base on a log, and it corresponds exactly to the base of a power, which is a base raised to an exponent. Okay? And then the argument okay. The argument, or we also call it the number, that's what you're doing the operation on. That's what helps you generate that exponent, okay? Therefore, the equation y equals log base 2 of x is the logarithmic form of x equals 2 to the y. Both of these equations represent the inverse of the exponential function y equals 2 to the x. Okay, so if you take y equals 2 to the x, graph it, and you take log base 2 to the x and graph it, you'll get the same, you'll get inverses of each other on the graph. Okay, putting it all together, the logarithm function y equals log base c of x is the inverse of the exponential function y equals c to the x. Y equals log base c of x means that y represents the exponent on base c, which gives a value of x. The base in exponential logarithmic form is the same, just like I said, as the base of the original exponential function. The result of a logarithmic expression is the exponent of the related exponential expression. A couple of restrictions. For y equals log base c of x, the restrictions on base c must be greater than 0, and c cannot equal 1. We'll show you why, right? Log base c is meaningless. The expression must contain an argument. So if you're doing this, log base c, you have to put an argument here. Otherwise, it doesn't do anything for you. Like exponents, logarithmic functions can be increasing or decreasing. The domain of logarithmic functions is always restricted to x is greater than 0 unless a horizontal reflection or translation is applied. This means that the argument is always restricted to values that are positive. You cannot evaluate the logarithm of a negative number, so log base 2 of negative 4 does not exist. You cannot evaluate the logarithm of 0, so log base 5 of 0 does not exist. However, you can evaluate the logarithm of 1, which is 0. Log base 7 of 1 equals 0. All right, folks. More on exponential and logarithmic functions. Let's start with a review of exponential functions. So we remember this. This is our classic increasing function with a base of 2. When I increase the base, what happens? It gets steeper, right? So what happens on a logarithmic function? We know that's the inverse. There it is, right? I'll throw in the mirror line here. What happens? So if the exponential function gets steeper when I increase the base, what should happen to the logarithmic function when I increase the base? It should get not steeper, but like, I don't know, like it doesn't rise up, it lowers down, right? So like that, as base goes up, it flattens out, it gets lower. Okay, so it's the exact opposite of what you would expect from the base. It gets steeper. Let's go to 3 and watch what happens. So it goes up like this, okay, and then watch what happens to the log. It goes down like that, and when we match the bases, they're still inverses of each other. They're mirror images across the y equals x line. Okay, what happens for the exponential function when I go less than 0? So let's go y equals, let's make our base, not less than 0. So let me back up. So y equals 3. Let's go to c equals 3, the base equals 3. Let's go to base equals 0.5. Well, we know that's going to create a decreasing exponential function. Okay, what happens if I go for the logarithm a base of 0.5? You should expect the mirror image, so 0.5, okay, and it's still a mirror image across that y equals x line, okay? Okay, so hopefully now you're seeing some relationships between the two graphs when we change the base values, okay? So let me turn this off and let me go over the example for the exponents, right? So we said when the c value, the base, is equal to 1, it's not an exponential function because it's a horizontal line. It goes up, c is greater than 1, it's an increasing function, c is between 0 and 1, so over here it's a decreasing function.
But what happens when c goes to negative? We get that weird effect. Remember this, right? When the base is negative and then the exponent, so we have dots on the positive side and dots on the negative side. So that what that tells you is that when there's a even number exponent, the dots are on the positive side, positive y side. When there's a negative number exponent, when there's an odd number exponent, then the dots are on the negative y side. So that's why you have that weirdness. So again, the base cannot be 0 for an exponential function. It has to be greater than 0. Okay, and it cannot equal 1. Okay, so remember that. It has to be greater than 0 and cannot equal 1. Well, what do you think is true about a logarithmic function? So let's put this back at 2. Take away that mirror line. If we said for an exponential function, the base cannot be 0, can the base be 0 for a logarithmic function? Let's take a look. No. Why not? Well, because if the base is 0, remember how to convert this, that would be 0 to the y equals x. Well, the only way 0 to the y equals x is if x itself is 0, and that's one specific case, but all other cases don't work, so poof, the logarithmic graph function, it disappears. So c cannot even be negative, right? Because how do I have a negative number raised to an exponent to equal a positive number? You can if it's an even number exponent, but for an odd number exponent, you cannot have a positive x value. So that's why there's nothing for a negative base for a log. So for a logarithm, c must be greater than 0. Okay, so that's where it first appears. Cannot equal 0, must be greater than 0. And then, why can't the logarithm base, why can't it equal 1? So let's reason this out. If the base is 1, I don't see a graph. So 1 raised to exponent y equals x. Well, 1 raised to any exponent is always going to be 1. So x must be 1. So it's one singular case. That's only one point. All the other cases do not work, right? If I pick a different x value like 5, how can I raise the number 1, a base 1, to an exponent y to equal 5? I cannot do that, right? So that's why for a logarithm, I cannot be less than 0, so I have to be greater than 0. There it appears. And then it cannot equal 1, but it can be greater than 1. Okay? So that's all my cases and restrictions for a logarithm, and hopefully you can see it not only graphically, but you understand it algebraically as well.
Okay, this is where we can understand how, a little bit deeper, how exponents and logarithms are related. So converting between the two forms, this is super important. Okay, we have to understand how this works, and we'll do tons of practice on the next page. We have to understand how this works, okay, before we can move on. Notice that a logarithmic function, y equals log base c of x, has an argument. Okay, you can also call it the number, but I like using the word argument because it's a very specific term, right? I'm going to stick with argument. So notice that a logarithmic function y equals log base c of x has an argument which requires a special set of rules to change. The result of a logarithm tells us the exponent. This is the result. So when you're executing a logarithmic function on an argument, the result that your calculator or your brain returns after you do the number crunching is the exponent. Again, the result of a logarithm tells us the exponent to which a given base must be raised to achieve a certain value. We read these equations as log base 5 of 25 equals 2. Log base 5 of 25 equals 2. And 5 raised to exponent 2 equals 25. 5 raised to exponent 2 equals 25. Okay. Let's take a look at this handy chart to show you how the two are related. Exponent, exponent. Look at the placement of where all these values are. Argument, argument. Base, base. Hey folks, we're going to continue um, this last part here when we're converting between two forms right here. The base is the base, the exponent is the exponent. See the commonalities, the argument's the argument. Another way to think about it, take the base, apply the exponent, you get the argument. In the above example, I take the base, which is, oh my goodness. Okay, take the base, which is 5. Okay, so take the base, which is 5, apply the exponent. Well, here's the exponent, 2. I get the argument, 5 squared. Well, that equals 25. I get the argument. Okay, take the base, apply the exponent, get the argument. Okay, next page. Here's the general statement about how the logarithmic form and the exponential form is related. Algebraically determine the unknown value in each expression. So this is where your knowledge of how to convert between logs and exponents comes in handy. So 4 to the, so if I have log base 4 of x equals -2, it's 4 to the -2 equals x. 1/16 equals x. Okay, log base 16 of x equals -1/4. 16 to the -1/4 equals x. Well, that's 1 over 16 to the 1/4, or 1 over the 4th root of 16 equals x. Well, what does that equal? X equals positive or negative 1/2. Okay. Next one, log base x of 9 equals 2/3. So x to the 2/3 equals 9. Okay. How do I solve this? I need to isolate x, so I'm going to raise x to the 2/3 to the 3/2 exponent. So I got to do that to the other side, 3/2. This is 1, so that's x equals 9 to the 3/2. Well, let's convert that to a radical. That is the square root of 9, so I'll put a 2 there. This is how I convert it. Square root of 9 cubed. Well, square root of 9 is 3 cubed, and that's 27. Okay, you try. Give these a try. Okay, folks, sorry about that. I'm going to do this. X cannot be negative, so I'm going to just scratch that out right here too. Sorry about that. Okay, here's a quick tip for you. We're going to keep going. The bases are the same, whether in logarithmic or exponential form. The exponent is the result of the logarithm. Remember those two key things, okay? Determine f of the inverse of f of x, okay? Expressed in logarithmic and exponential form. Okay, remember we're swapping x and y values. Okay, so I'm going to write it this way. Okay, that helps me see it better. So that's 1/2 to the exponent x equals y. Okay, so I have something in exponential form. Let's write the inverse. We're going to swap. And then let's write this in logarithmic form. Log, what's the base? The base is 7. What's the argument? X. The exponent, the result that returns is y. Okay, you give it a try. Okay, go to the next page. Almost there. This is a long introductory lesson, okay? The logarithm, let's talk logarithmic form of y equals a times c to the x. To convert the exponential form y equals a c to the x to logarithmic form, isolate the exponential form y equals a times b to the x as y over a equals b to the x. It's super important that you isolate the exponential form. So you're writing the power by itself. Okay. 2. Convert y over a equals b to the x to logarithmic form. Okay. So how do I convert this to logarithmic form? The log, what's the base? B. What's the argument? Y over a. The result of an exponent is always, so the result of a logarithm is always the exponent. Okay, you try. Let me do the first example here. So if I divide both sides by 4, I get y over 4 equals 5 to the x. Isolate the exponent. Sorry, isolate the power before you convert to logarithmic form. So the log, the base is 5. The argument is y over 4. And the result is the exponent. Okay. Okay, give the next two a try. Okay, the exponential form of y equals a log base c of x. To convert the logarithmic form y equals a log base c of x to logarithmic form, isolate the logarithmic form y equals a log base c of x as y over a equals log base c of x. Convert y over a equals log base c of x to exponential form. So in this case, I'm going to rewrite it like this. Log base c of x equals y over a. Okay, what's the base? Base is c. What's my exponent right here? Y over a. And the result there is the argument x. Okay, let me do the first one for you. Okay, this one, the first one, doesn't require a rearrangement. Okay, so this one, the base is 2. The exponent is the argument. And the result is y over 3. Okay, oh, let me start over. The base is 2. The exponent here goes there. And then the argument of the log, right, becomes your result now. Okay, better. Let me do c as an example, and you can try the other two. I'm going to divide both sides by 7. Okay, the base is b. The exponent is x over 7. Okay, x over 7. And the result is y. Okay, give the other two here a try.